The first thing I want to talk about, so I'm going to focus today on this issue of thermal integration. Just as sort of a straw example of this, imagine we think about an SOFC, so an SOFC stack. Imagine we put in some fuel and we put in some air. And out of this fuel cell, we're producing exhaust gases. Come back to some of the details of that in a second. But one of the things that is true of an SOFC is it has to operate at fairly high temperatures. We're talking about 500 to 850 degrees C. And when we've been looking at fuel cells as a black box, we've been thinking about this as, okay, we're going to produce some electrical power, and we're also going to produce some heat. When we've been talking about that, we've sort of been thinking about it as an isothermal thing. So imagine, instead of giving a range, imagine we have this thing operating at a specific temperature, 750 C. And the fuel and air are going in at 750 C, and the exhaust gases, they're coming out also at 750 degrees C. Think about how we would manage this, right? So we could heat up the fuel and air to 750, but then how do we get rid of this heat? So imagine we put a control volume around our process and we think about, okay, what does this Q dot really mean? So far, I've been treating it conceptually, but how do we actually get the heat out? In my laboratory where we do these individual cell tests, there's not much to this, right? We've got a little tiny cell, has a massively high surface area, and we have a furnace around it. We keep it at this fixed temperature of 750 C. Q dot is just whatever it needs to be in order for the cell to remain constant temperature. But think about what we're doing in a real system. We don't have one little cell in a furnace. We've got a whole stack of cells. As that gets bigger, we're producing more thermal energy inside. As we increase the volume, that production of thermal energy is getting bigger and bigger by the volume of our system. But the surface area is only scaling as the square of the size. The surface to volume ratio of a real SOFC stack is really small. There isn't really a way to get the heat out, to have a Q dot coming out of a fuel cell stack in the same way we've been thinking about it. It just doesn't exist. Okay, so if that's true, we can't flow thermal energy magically out of our stack. How do we make the energy balance? And I think the only way to think about that is we have to have a temperature difference. So this going in has to be less than 750 degrees C. And all these exhaust gases coming out, maybe they're greater than 750 degrees C. And now all of a sudden we have a way of removing thermal energy. So this gets to sort of one of the essential kind of dilemmas or whatever that you have with a SOFC. You think about our requirements. We have to keep the system hot because the thing has to operate at high temperature. But as I showed you last time, we have to get rid of the thermal energy. So we have to keep it hot, but we have to cool it. Sounds like an oxymoron. As chemies, I think we're used to that idea, right? Because keeping something hot, that has to do with temperature. Cooling something has to do with thermal energy and enthalpy. That's the essential issue. How do we get arrange the situation where we have cooler gases going in, hotter gases going out, removing that thermal energy, but keep the temperature at 750. So we talked about some of the conditions that we were thinking about with our data center example. We had a cell voltage of about 0.7 volts and a utilization of 80 or 85%. Let's just set it at 80% for this example. One of the things we found out is under those conditions, only some of the enthalpy would be converted to electrical work. So our system looks something like this. The start of our system. Here's our SOFC. And let's say it's operating at 750 C. It's producing electrical work. This is where our 20 kilowatts is. And are feeding into this some air. And we're also feeding in fuel. And for the moment, let's think about this as hydrogen. So we're going to come back to the issue of fuel reforming and methane and all that stuff. But for the moment, let's imagine that we're feeding the fuel cell hydrogen. When we say we're operating at 750C, what you might imagine is that as gases go through, they're going to come to some type of thermal equilibrium with the solid surfaces that they're in contact with. And that's generally the case. So as this thing's operating at 750, we've got all this radiative heat transfer going on. And by the time the gases leave, they're leaving more or less in thermal equilibrium with the solid surfaces that they might come in contact with. So these gases are coming out at 750C, hydrogen, H2O. We may also have some H2O coming in too, and I'll come back to why that is in a bit. We're going to come out with nitrogen, and we'll also have some oxygen left over. We don't burn all of the oxygen for reasons I'll talk about in a second. So we've got depleted air, we've got unreacted fuel. We know there's some unreacted fuel because we're only at 80% utilization. So that means 20% of whatever hydrogen we feed in is going to come back out. For various reasons, which I'll talk about later, it's hard to recycle that hydrogen. So in practice, it means that we're probably going to be feeding this to some type of post-fuel cell combustion process. We'll just draw it as a combustor. And what's coming out of this is exhaust. And contained in this exhaust is nitrogen, oxygen, and water, gas. There's no hydrogen left because we're just going to burn up all the rest of the hydrogen. And the temperature is going to be greater than 750 degrees because the combustion is going to heat it up even further. So coming out of this 750C, coming out of the combustor, it's even hotter, whatever it's going to be. How are we going to get thermal energy out? These gases going in have to go in at a lower temperature. And what that lower temperature is, that really depends on a lot of different things. But in many cases, it's something that we're going to specify because the fuel cell materials, for example, the electrolytes that we're going to use, their conductivity is really sensitive to temperature. And also the kinetics of the reactions of the electrodes are really sensitive to temperature. So we don't want the gases to go in too cold. It needs to be minimally the temperatures at which these cells materials will actually operate. And for an SOFC, that's somewhere around 5 or 550 degrees C. Another issue is thermal stress. You get stress fracturing if you suddenly cool something. It's just like you take, a hot piece of glass and you plunge it into water, it's just going to shatter. And so usually this has to be whatever minimum operating temperature the fuel cell will ever see, that is the minimum temperature that the gas is going in can be. So this might be, something like 550 degrees. And that's usually something that we're specifying as part of the materials of the cell. So this comes back to, what are the properties of a fuel cell and how do they depend on temperature and things like that. And we're going to come back to that later. But for the moment, think of it as there is a constraint. We can't go below a certain temperature. So that's sort of the constraints on the fuel cell. We've got to cool it, so we need a temperature difference. We have sort of an upper operating temperature, maybe 750C. We have a lower feed temperature that we can deal with, which is 550C. I already know how much power we're producing. We know what the cell voltage is. And because we've specified cell voltage, we've specified fuel utilization. So we can do all the stuff we did the last 2 weeks. We can calculate exactly how much hydrogen is going into the system. We can also calculate how much of that thermal energy we have to get rid of. So what is our degree of freedom here? I mean, how do we control cooling? The only thing we have left is the airflow. And so the airflow is kind of one of our question marks.
I had a question about this degree of freedom you're talking about. That's like the airflow. We're using air to cool the cell. Is that like a separate stream that isn't drawn here? Or is that just are you saying that's just like the function of the air as it's going into the cell anyway? Does that make sense?
Yeah, so typically, it depends on the types of fuel cells. Some types of fuel cells, you have a separate stream where you feed in a cooling fluid that actually does this job, right? Yeah. It's really hard to do that in an SOFC. Part of the reason for that has to do with the laminar flow. The other thing is just the complexities of manifolding a second fluid that has to intertwine through all the cells in your stack. That is done in PEM systems, but not in SOFCs. So instead of having a separate gas stream, you just feed in extra air that you wouldn't need from a stoichiometric standpoint.
Okay, I see that now. Okay, thanks.
Is it possible that we could have a scenario where oxygen was the limiting reactant and we had hydrogen instead of oxygen?
I think practically no. And the reason is basically at the end of the day, air is free. So if you're going to feed extra stuff in there to achieve cooling, which is what we're really doing, it's the air that costs nothing to get more of, whereas the hydrogen it's our valuable resource. So I'm going to just start putting a question list over here on the side. What is the airflow that we have to push through this thing in order to keep everything cool? The other question is, how do we arrange these temperatures? How do we get the air and the hydrogen to 550 in the first place?
Could you possibly like combust some of the H2 beforehand and feed that exhaust around to a heat exchanger to preheat the air?
Think about our goal here. We're producing electricity and we're producing thermal energy. And now to get up to 550 C, we have to put in thermal energy, which seems like the opposite of what we're actually seeking to accomplish. Hydrogen is your primary resource. If our fuel cell is operating at 80% utilization, that's basically saying we're wasting 20% of it. Now we're going to waste even more of it in the overall process in order to heat the gases. That lowers our effective utilization of our process below 80%. There's any way to do this without using any more resources? We've got this exhaust coming out, right? And it's coming out at greater than 750 degrees. What do we do with all of that exhaust that's coming out at like 800 degrees?
Well, you can recycle it back to the input stream for the heat, right?
Ah, okay. Now I think you're onto something, right? Because we've got all this thermal energy. In fact, all the thermal energy we wanted to get rid of is, where does it end up? It's contained in the enthalpy in that exhaust. So what if we put it to use? So imagine we take that stream, take it over here, and I'm going to put it through a heat exchanger. This temperature here is greater than 750. The main point of this heat exchanger is I'm going to dump that heat on somewhere else. Where do we need some heat?
You could use it to heat your input streams.
Let's do that. Here's air. For reasons I'll get to in a bit, we often don't feed dry hydrogen into a fuel cell. It's going to have some humidity in it, and it depends on the temperature. But let's say it's 20 degrees C. It's going to be about 98% hydrogen and 2% H2O. And I'm going to start labeling the stream. So that's stream 1. Let's call the air stream 2. We're going to heat this hydrogen up to 550 degrees. And I'm going to call that stream 3. And likewise, the air, I'm going to do the same thing. I'm going to heat it up to hot enough temperature. Let's call that stream 4. This will be stream 6, stream 5, call this stream 7, and I'll call the exhaust coming out of the heat exchanger stream 8. First of all, let's think about whether this is realistically possible. Maybe you've done this in 340 where you draw like a position versus temperature diagram within the heat exchanger. On the left side, we know the temperatures on the left side. So the exhaust is coming in greater than 750. And the hydrogen and air are coming out less than that, 550. And then on the other side, the hydrogen and air, presumably they're coming in at ambient temperature. So this is like 20 C. And so as this air and hydrogen goes through, it's heating up as it flows through this way. And the only way that can happen is if it's in contact with something hotter along its entire flow path. So that means our exhaust has got to be cooling off, but not cool off down to 20 degrees. Is this realistic? Is the exhaust flow going to be, big enough basically to be able to support this much heating? in a sense, the two streams in terms of their mass flows are identical. The exhaust coming out is equal to the stuff going in. So the nitrogen going in the air is the same nitrogen coming back out again. And the hydrogen and oxygen go in, it's the same atoms forming all of the water, which is coming back out again. Even though heat capacities of water and hydrogen and oxygen are not all the same, they're kind of in the same ballpark. If the heat capacity of the outgoing stream is anything similar to the incoming air, it is going to cool down by a similar amount. So if we're, going from 20 to 550, there's a 200-degree difference in temperature, you might expect the stuff coming out to be like 200 C or something like that. So I'm going to add this to our sort of list of growing questions. We need to figure out how much airflow we need to keep the stack cool. We now have a new question, which is, what's the exhaust temperature? Then we can start asking questions like, what are the temperature profiles in the heat exchanger? What kind of heat exchanger area would we need? All the, for sizing this thing. And so this sounds like a bunch of like Chemi 310 problems, right? And that's exactly what it is. So let's digress for a little bit on that and walking through like exactly how do we go about doing these energy balances to address some of these questions about the process as a whole.